Imagine a statement G, a statement that revolutionized how we think about math forever.
G looks something like this. If we assume this is true, then the statement is false. So we have to assume it's false, but that would make it true. And we could go on like this forever, because the statement is a self-referential paradox.
Except G is not a verbal paradox, but rather a self-referential number sequence. Since numbers generally don't talk about themselves, the logician Kurt Gödel created a system known as Gödel numbering, which converts statements about math into math.
Gödel encrypted the statement G, which is actually I cannot be proven, into a number. And since assuming the statement is false leads to a contradiction, then it can't be false, so that statement has to be true. And thus G is a true, unprovable mathematical equation.
So did G break math? Well, no, not really. And it's important to articulate what G actually proves.
First, we have to understand that an axiom is essentially a rule of mathematics, and a proof is an argument that shows that a certain statement is true. G gives rise to Gödel's incompleteness theorem, which says that in a consistent mathematical system, there are a myriad of statements that can be derived from the axioms, some true, some false. But inside that system, we will always find statements which are true but are not provable by the axioms in that system. We only know they're true by going outside that axiomatic system and looking in. Even if we try to think about those unprovable statements as axioms themselves, as rules within the system, we would still get more unprovable statements, and that would go on and on forever. No set of axioms will ever completely explain every true statement in a system, hence Gödel's incompleteness theorem.